Prior to the launch and successful commencement of operations of the James Webb Space Telescope, I made 3 Thunderbolts videos in which I discussed Webb's significance in the context of electric universe cosmology issues, and I made several predictions of what the Webb Space Telescope would reveal. This is the second episode to report on success in relation to those predictions that emerged in the very first release of Webb images. Before proceeding with an analysis of those images, I need to deal with a few matters to set the scene. Redshift refers to an increase in the wavelengths of light, measured as a shift in the frequency of spectral emission or absorption lines that are characteristic of particular elements or chemical compounds, when compared to the wavelengths emitted by those elements or compounds in the laboratory. In standard model astrophysics, the redshift of a particular object can be a mix of 3 separate components. The first component is cosmological redshift. That expression refers to an object's redshift that is due solely to the expansion of the universe, the expansion of space-time itself. This results in a recessional velocity between galaxies that are at rest in their local frame. The second component is redshift arising as a Doppler effect from the object's motion in relation to other objects in their local frame. Such motion is referred to as proper motion or peculiar motion. The third component is gravitational redshift, which refers to an effect predicted by general relativity, namely the lengthening of light waves traveling out of the gravitational field of a massive object. The first 2 components give rise to a level of confusion for lay people, precisely because the word velocity is used by astrophysicists and cosmologists in both contexts. The word velocity is routinely used to refer to the rate at which galaxies and other extragalactic objects are receding on account of the expansion of space, rather than their proper motion. On the other hand, the word velocity is also used to refer to proper motions inferred from small differences in the redshifts of, for example, interacting galaxies, or galaxies within a galaxy cluster, or differences measured within a galaxy or cloud. And in the case of galactic jets, much larger differences in redshift are correctly attributed to proper motion. When an active galaxy with a particular redshift has bipolar jets, one jet will have lower redshift, indicating that matter in the jet is traveling towards us. The other jet will have a higher redshift, indicating matter in that jet is traveling away from us. Nevertheless, in the standard model, the redshift of all galaxies and quasars beyond our local universe is almost entirely cosmological redshift, arising from the expansion of the universe. It was Hubble's observation and the spectral analysis by Milton Humason that established the correlation between luminosity and redshift. In every direction that Hubble observed, decreasing luminosity correlated with increasing redshift. It was the interpretation of redshift as a Doppler effect arising from recessional velocity which led to the conclusion that the universe was expanding. Simple extrapolation backwards in time drove Gamow and others to conclude that the universe must have started with what later came to be called the Big Bang. It is commonly said that Big Bang theory is based on 3 main categories of observational evidence, called the 3 pillars: the expansion of the universe, proved by the Hubble redshift luminosity relationship, the cosmic microwave background, and the abundances of the light elements. However, it is the first of these that is the essential foundation of Big Bang cosmology. If the universe is not expanding, then the whole basis for theorizing about the consequences of a Big Bang is removed. Make no mistake, it is the expansion of the universe, embodied in the Hubble law, that is the essential foundation on which the whole of Big Bang cosmology is erected. If the observed correlation between redshift and luminosity was not due to a Doppler effect, but due to something else, as Hubble suspected and as Halt and Arp demonstrated, then that foundational axiom is destroyed, and with it, the vast edifice that is Big Bang cosmology collapses. Galaxies and quasars with significantly different redshifts may appear close to one another on the plane of the sky. However, in the standard model, this must be a chance alignment, because a significant difference in redshift must mean that the objects are in different parts of the universe, such that any physical connection between them would be utterly impossible. Similarly, in the Standard Model, viewed from Earth, it would be utterly impossible for a high redshift object to be in the foreground of a low redshift object. This is a bit like the proposition, all swans are white. Just as finding a single black swan would disprove that proposition, finding a single example where objects with significantly different redshifts were physically connected, or where a high redshift object was in front of an object with much lower redshift, would destroy the essential foundation on which the whole superstructure of Big Bang cosmology is erected. Of course, that analogy is imperfect. In the case of quasars and high redshift galaxies, the astrophysicists have never, in fact, seen any of these objects up close. They do not know whether the redshifts of these objects represent a distance arising from expanding space. They have never demonstrated that any of those swans are white. In my June 21st, 2021 Thunderbolts video, I noted that, quote, "ARP's research into high redshift quasars shows they are local," unquote. That is, quasars are not at the extreme distances indicated by the Standard Model interpretation of their high redshift. I made the following prediction, quote,
"So my first prediction is that the James Webb telescope will support Halton ARP's research, which shows plainly that high redshift quasars are born in pairs and emitted in oppositely directed jets along the spin axis of a low redshift active galaxy. They are not at the edge of the visible universe. They are in the neighbourhood of their parent galaxy. Therefore, they are not incredibly distant, bright and large. There is no superluminal motion. They are nearby and youthfully faint."
Unquote. A final adjudication on that prediction will require a substantial accumulation of Webb data. That will take years. And yet Webb's first science images provide a vindication of ARP's basic contentions that cosmological redshift is intrinsic and not due to the expansion of the universe, and his theory of quasar birth from active galactic nuclei. The first piece of evidence arises from the Webb images of Stephan's quintet and a quasar appearing in the main field of the galaxy. Quasars became central to ARP's research program. He gave an account of the origins of that research program in his contribution to an edited volume, Against the Tide, a critical review by scientists of how physics and astronomy get done. Quote, "Quasars were discovered in 1963 by radio astronomers, and optical astronomers rushed to observe them because they assumed their high redshifts meant they were at great distances, and that the nature of the universe would thereby be revealed. The Caltech radio astronomer who isolated the positions of the first quasars asked for telescope time to observe their spectra and obtain their redshifts. He was told only certain of the faculty could observe with the 200-inch telescope. Those select few went on to measure the spectra and reap the headlines, and the original discoverer left the field in disgust. As a Carnegie astronomer, I was observing on the telescope, but the radio positions of the quasars were kept secret, and so I did the next best thing, photographing peculiar and disrupted galaxies to see how they were formed and evolved. Ironically, in the end, they turned out to be surrounded by quasars, which were obviously not out at the edge of the universe. That news was not welcomed by the observers, who had inflated their reputations with discoveries of a new, quote, most luminous object in the universe every few weeks, unquote. It was ironic indeed, because quasars took center stage in the evidence of anomalous redshift assembled by ARP and others over the following decades. This is a Hubble image of Stephan's quintet released in the year 2000. It's a composite of 3 images, obtained by Hubble's Wide Field Camera 2. 2 were in visible light, and a third at 814 nanometers in the very near infrared. NGC 7319 is the galaxy at the top of that image. In the early 2000s, ARP was part of a team that identified an ultraluminous X-ray object as a high redshift quasar apparently in the foreground of NGC 7319. That discovery was announced in a paper published in 2005 entitled The Discovery of a High Redshift X-ray Emitting QSO Very Close to the Nucleus of NGC 7319. It's required reading for all cosmologists while looking at the relevant images. This is a portion of the 2000 Hubble image, with processing to increase contrast and saturation, which appears in that paper. The galaxy NGC 7319 has a redshift of Z equals 0.0225, whereas the quasar has a redshift of Z equals 0.2114, numerically almost 10 times greater. On the assumption of the Standard Model's redshift distance relationship, and using Ned Wright's calculator with default values, NGC 7319's measured redshift of Z equals 0.0225 places it at a look-back time or distance of about 311 million light-years when the light captured by Hubble was emitted. On the other hand, the quasar has a measured redshift of Z equals 2.114, placing it at look-back time or distance of about 10.58 billion light-years when the light captured by Hubble was emitted. On the Standard Model, that is some 34 times farther away than NGC 7319. Even on the Hubble image, it was obvious to ARP that the quasar was in the foreground of NGC 7319, and therefore closer than NGC 7319. Look at the dark dust lane that passes on a diagonal path that visually encloses a portion of the quasar. Not only did the quasar appear in the foreground, as this image plainly shows, there is also a V-shaped jet extending from the core of the galaxy to the quasar. The existence of that feature, previously identified by mainstream astronomers, was confirmed in radio observations by ARP and his colleagues. ARP writes, "This is the only system found so far in which there is the possibility of demonstrating even more clearly that the quasar and galaxy are interacting. It was striking evidence that the quasar had been ejected from the nucleus of NGC 7319. ARP's Standard Model critics insisted that the quasar was at the unimaginably enormous distance indicated by its redshift and therefore had to be a background object, but so bright that it shines through the entire dust and plasma of the disk of the galaxy. And as for the jet, well, whatever." Subsequent to that paper, in 2009, a further Hubble image of Stephan's quintet obtained with Hubble's upgraded Wide Field Camera 3 was released. Here is the indicated portion of that 2009 Hubble image with the quasar marked by an arrow. That image did not change the arguments, notwithstanding that it seemed even clearer that a dark dust lane passed behind at least some portion of the field of the quasar. The dust lane has a ragged edge. Perhaps there was a deviation of the dust lane at precisely the point where the quasar appears. As we shall shortly see, Webb images of NGC 7319 within Stephan's quintet now put the issue beyond any reasonable argument.